Hi, and this time we will talk about the theory related to the system of interruptions in the microprocessor, okay? Something that is it is based on an interrupt logic that has this kind of design. You see, it is based on collecting all the possible sources of interruption from the EEPROM, the analog digital converter, to the transmitter, from the transmitter from the timer one, and many other peripherals. So in the main idea behind this thing is that every peripheral is able to interrupt in some way or another the flow of the main program, generating the interrupt to the CPU and jumping to the interrupt service routine so that this interrupt can be acknowledged and served. Okay, and we will take the example of the external interrupt, the simple external interrupt, so that we will talk about the external interrupt flag, the external interrupt enable, and naturally the general interrupt enable bit, configuration bit, to be able to jump from the main loop and so attend and acknowledge interrupt sources in some way or another. That is the purpose of this video. Okay, so this idea of the interrupt to the main program deserves a kind of an explanation that is perhaps better in this way as a video recording using the whiteboard than, commenting some slides. Perhaps this way is better. Even if you have the pictures here, I will try to explain what is happening here. If you imagine the real circuit that is behind the idea of detecting an edge, okay, an active edge that you like to detect to trigger some kind of operation. Okay, so this is the main program, as you know very well. For example, initialize the system and then pull the inputs that are not interrupts, just pull inputs that you like to know the level of the signal when it happens in this loop, you see. Then perhaps if you are running a finite state machine, which is our case, you see, what you have in mind is to run software functions, the state logic function and the output logic function. And perhaps why not? Because you have something else for processing information. You like to operate as well here, who knows, the data path. For that is the main loop, okay? So the data path as well goes here as another function. Data path for counting or for calculating the temperature of a given sensor that has been acquired, reading inputs or whatever, So that is the loop time. And well, what is that happens here is that you are not aware. If someone clicks a trigger, you are not aware in which time that is going to happen. So this is what the interrupt system tries to solve. To be aware, to detect exactly the time when someone triggers a button so that you can start timing or you can start printing or whatever you have in mind to do in your system. So right, this is the main loop. So you have to detect, for example, this time TA, when someone clicks a button. And to do that, you need hardware and you need software as well. Just a mix of everything in some way, like is presented here in this circuit. So let's try to imagine a little bit what is happening here, section by section. For example, you like to detect from an external pin, the rising edge of some event. So very well, okay? So when you click a button, something like this. So this indeed is an analog signal because it's not something that belongs to the memory of the microprocessor. It is an external signal, a voltage. So and if it's a voltage, you may very well say VI in time. So this way. And this signal, if it's, for example, from an external push button, is going to look like this. You have the VCC, then you have the push button, and you have a resistor to ground this node. Okay, so when you click, you generate this signal, but logically, perhaps because it's a button, it is the connection of a metallic part to some metallic contacts, and there is going to be a bouncing, and who knows the shape of the real signal is going to be. Okay, that is depending on the pressure, is depending on many factors. So indeed, the kind of signal that you have as an input, even if you are imagining that clean edge, is not so. It's going to better look like this. You see, you click here, you click, you see, for example, here is when you click the button, you see, there is when you click, you press the button just now, and you know, you had previously you had the clear zero, but now you know the signal evolve, and logically if you keep you see, this is the clicking time, this is your clicking time, all the time that you are holding the button clicked, all right, and then you release that. Okay, here is when you release. Well, clicking time is perhaps up to this point. Yeah, that's a lot better. Click time, this time when you are holding the button, and then when you release, oh no, this is the release time. Okay, this is when you are taking your finger from the button, something like this. Okay, you can see that very well using an oscilloscope, and that kind of timing, and it's in the range of milliseconds. Okay, so this signal is quite long if you imagine that in terms of microseconds, or yeah, you do not to mention nanoseconds. You see, it's like a lot of time. Okay, even if you simply click a button. So that's the real signal. So what we have here to avoid all these complications, okay, is the replacement of a conventional buffer or a conventional gate that you know that works like this. You see, a voltage between 0 and Vi low maximum is understood as a 0, okay, and when you have a voltage really between Vi high minimum and VCC, you have clear a 1. So because it's a buffer, for example, this voltage is repeated at the output, and this output is something in between VCC and V0 high minimum, and if this output is 0, is a voltage between 0 voltage, you see, and V0 low maximum. That is the transfer function, you see. That is the typical transfer V0, you see, V0, Vi transfer function. The typical from one of the gates that we are usually using, you see, from P1 and P2 and so on and so forth. So we have something better here, okay, just to interface and clean in some way and avoid complications and electrical noise. We have something better, and this something better is a logic gate that is looking like the same, a buffer, you see, but has this internal symbol that is indicating that what you've got here is a Schmitt-trigger comparator. Okay, and a Schmitt-trigger comparator is a kind of a gate that is ruling, is managed using this kind of window, and this kind of window has a proper name. This is the typical hysteresis window, and the way it works is like this. You see, you have a voltage right from 0 to VCC. This is what you can apply, a voltage from 0 to VCC as maximum. And look at this, if you start at 0 and you go up, now you can go beyond this Vi low maximum and nothing happens. You see, nothing happens. The output is still 0. Okay, it is not until you are reaching the Vi high minimum then, you know, the output goes immediately to a logic level 1, this way, and then it is kept like this even if you are arriving to VCC like that. So if you do that in time, for example, it's going to be like this. You are clicking here and then the wave evolves, but you know it is climbing in some way, or it is Going down again, doesn't matter. You are here in this region, you see? You are clearly in this region between the dot A and the dot B, so you are here. So because you are here, you see, you are kept with a 0, okay? And then you are reaching this point A and you have a 1. Very well. So if you have a 1, you see, it doesn't disappear immediately as it happened in a conventional gate, or indeed in a conventional gate you know nothing because you are perhaps in the middle of the forbidden zone, and this is something that you have to prevent because it's not even a digital value, a clear 0 or a clear 1. You know nothing about the forbidden zone, but here it is stated like this. If the voltage is evolving in some way, you see, even if it is going upwards up to the BCC or going downwards from this voltage, doesn't matter. You see, you are keeping the 1. You see, so you keep the 1 down the voltage that we are naming B. So you see, all this evolution of the input doesn't matter. You see, the signal is evolving this way because of an spurious noise. You don't know very well why you have this random behavior of the electrical voltage, but this is the true story here. So even if the signal is evolving, the point is that if you are using this gate, the voltage is kept clearly high. You see, look at this, from A down to B you have a clear 1. So that is pretty much a perfect digital signal. This is what you want. And when you are reaching the dot B, you see this VI low maximum level, if you like, the B voltage, then you see it goes down this way. And you've got a 0 again. So you keep the 0 all the time, doesn't matter. You see, you keep the 0 unless you are again up the dot A. So you see that's the way it goes. So this is a great advantage. It has an internal circuit that is based on this idea of a Schmitt-trigger hysteresis, and it is possible using positive feedback to get this kind of window that solves this complication of the forbidden zone. Now that's good to know, okay? So yes, by means of this device, when you click, you can imagine very well you have this kind of the bouncing circuit to get rid of bouncings and everything else, and you get something important here. It's a clean digital signal. So here, you see, you may say in this wire at the output of this Schmitt-trigger buffer, what you've got is a clean digital signal, pretty much the same that you've been used to, you see, all the time for processing whatever you like in the digital world. So that's it. Then what? Well, here you have clearly two edges, the rising edge and the falling edge, because you click the button and you release the button and you are generating these two transitions. So naturally you like, for example, to detect a single edge of interest. Let's imagine that this edge of interest is just the rising edge. Okay, but you can select that very well, which is your edge of interest, because you have a shore gate that is acting, like this. You have a control input. So this is X, this is Y, this is a control input, and if you have here a 0 in this configuration bit, you see external interrupt 0 edge. So you see, you can get the edge of interest that you like, the rising edge or the falling edge. So with the 0, you keep the rising edge, okay? You select the rising edge, and with the 1, because then you know the Y is going to be not like the X, but the X not. In some way you are reversing the situation, and for the same price exactly, the next circuit that is here, you see the edge detector. This is the edge detector. The edge detector that you can very well organize in some way like this, a single inverter with a propagation time and an ideal and with using this simple or conceptual edge detector, you can manage to get the edge that you like. Look at this. This is the X, right, from the buffer. This is the Y, just a photocopy. Let's imagine that is ideal buffer. That one is ideal the same. So then W, no, it's just a knot, right? It's a knot. But a knot with an associated propagation time in the domain of a nanoseconds because it's a single gate. So Y has the shape of, W has the shape, the opposite shape, the inverted shape of the Y, but delayed this TP time. So when this is 0, this is 1. When this is 1, this is 0. When this is 0, this is 1. Very well, a knot, but delayed, you see? So Z is nothing but, you see, the logic operation W and Y. And W and Y, you see, looks pretty much like this. You see, 0 and 1, 0. Then 1 and 0, you see, 0. 0 and 0, 0, 0 and 1, 0. You have zeros almost all the time, except in the delayed Y time where this signal is still holding the 1 for some nanoseconds. Here you have a 1. Look at this. You have a 1 and Y is still a 1. Well, Y is a 1 and W has not yet flipped toggled to be 0. So you have a 1 and a 1, and this and that is very fast, as you can imagine here in this ideal circuit, can detect that thing and generate teeny pulse. But you know, a teeny pulse, you see, that is just the set input of, for example, to make it simpler, an RS latch. And you know how an RS latch works, right? Remember, RS, and this is Q in the future, the Q in the future, that after some nanoseconds, 0, 0, keep the value, 0, 1, save a 1, 1, 0, save a 0, and 1, 1 is not defined. Very well, so look at this. You may imagine that here you have a 0, 0, 0, that is 0, so imagine that the Q is 0, right? No problem, you can imagine that very well. But when Z goes high, you have a situation where you have a 0 in the R and a Z1, so you are saving a 1. Look at this green waveform, you're saving a 1, so, and then you see immediately, just a few nanoseconds later, you have 0 and 0 again. So, but you know, because this is a 1-bit memory cell, this one that is saved here, you save a 1, is kept high as long as, or for as well, it is high, and it's not going to go low unless you drive the R signal, the R input, you see? And you are going to do that later on by software with a given instruction. For example, when you say in your code something like this, external interrupt flag equals 0, you do that in C, semicolon. When you do that in a software instruction, you, in some way, the circuit is driving this to be a 1, you see, and then if you have a 0 and a 1, now you are, you see, clearing, you are resetting, you see, you are saving a 0 that way. So when you do that later in the software, this flag goes down to 0 and it becomes as it was at the very beginning. You see the point? So that's it, you see? So you've been able to save a bit of information that is high ever since it has been detected the edge, you see, in the X signal. And that is the way it works, and this is exactly what you want. And the only thing now, perhaps, in order to comment that, is that you can program that if this bit, okay, you can program whether this bit is enabled to generate a vector interruption or not. And you can do that with the interrupt, external interrupt 0, interrupt enable bit, just another bit in another interrupt configuration register. So you do that. If this is 1, for example, if this is what you do in the software, if you are doing that in the init system, the one that you've got here, because you had this edge, is able to go through this OR and generate, if you have the general interrupt enable also enabled, you see this one that you've got from this external interrupt goes through the logic of the interrupt system and generates an interrupt vector. And what is exactly the meaning of this? Well, in the same way, because we are just here, you see, studying this logic interrupt circuit, you can do that from this external interrupt 0 the same way that you can do that from the external interrupt 1, the 2, the RB, the EEPROM, the timer 0. You see, if you are thinking on the timer 0 that we will study very soon in the next project. So if the timer 0 works pretty much the same, you have a timer 0 overflow, and this overflow, this terminal count is connected to some kind of RS latch the same way like this to generate a flag that is kept high until you reset it the same way. So you can enable this flag from the timer and generate the same kind of interrupt vector, okay? And what is the meaning of this if you allow interrupts to the main program? Now, the meaning is that something like this happens if you have allowed that using the correct values in the configuration bits. If you have done that, look at this. The system is running through the loop at very high speed, for example, 10,000 times per second, okay? It's executing the main loop. And then what happens here? Let's see that in time, because if not, if you don't do it in this way, perhaps it's a little bit difficult to understand. Look at this. You have an edge, right? Let's go to the beginning. You have an edge. The edge is detected like this, because this signal is very clean. And this edge generates this Z, and this Z establishes, you see, just in a few nanoseconds, the Q, this flag to be 1. So, at this time TA, when the edge of interest just happens, at this time TA, the main loop is running, and anywhere in the loop it's interrupted, just at this time TA, you see? So here is when the interrupt happens. Here, you see? Here is the external interrupt 0 event. And in this time the event is just a rising edge. This is what you have here. And then what? Well, if you allow to jump this way to the interrupt vector, well, the main program has this kind of call to attend an interrupt and goes to another section of the code that is called the interrupt service routine, as you see here, where you have several instructions and several tasks to do. But, you know, it is going to be a time, it's going to be an instruction like this, because you see, if this interruption has been, it is possible because you have an external interrupt event, you will detect that, okay, because you will ask if this, in some way here, you will ask if the external interrupt flag is 1, if that's the situation, if this is yes, okay, if this is yes, if this is the flag that, because you see, you have many sources of interrupts, but at the time TA, only one of them has been the source of interrupts, okay? At this time, the interrupt cause is because of the external interrupt. So you will ask that in this kind of, in this piece of software, you will ask if the external interrupt flag is high, and if yes, you are going to do that thing. For example, here you will set, basically what we do here in this introductory course is basically a very few things. We will set the software hardware variable bar, you know, bar what? For example, if this is a clock, who knows, or if this is the start button, we will name that. bar start button or start transmission flag. We will set that variable here, and then we will clear, you see that one. We will clear the hardware flag, the int0 interrupt flag equals 0. And after executing this instruction, this is, for example, at the time TB, okay, if this happens later on after executing some instructions in C or in, well, not in C, you know that this happens in assembly. So at the time TB, you do that. Well, so doing that at the time TB, you see here, it means that the reset signal is driven so that the flag is finally, you see, is finally cleared. So this is the time that you have had with the interrupt detected, okay? And this is exactly the time when you have decided to clean this flag so that later on another edge is possible and another time another interrupt. And that happens, for example, when you have a cyclical clock here. So every time that you have a rising edge, you have a new interrupt. That's it. Okay. That's more or less in time. You see, it takes 20 minutes to explain that, but it is of interest because we will talk about these and these basic ideas once and again. Okay, so we will configure in the init system some of these values to prepare and organize the possibility to jump to the interrupt vector, and then in the interrupt vector itself we will talk about cleaning the flag, the hardware flag. So you see, for us to finalize this explanation, we will talk about this external interrupt 0 interrupt flag as a hardware external flag, because you know we will rather prefer to talk about the other one. You see, the one that is set here as well, as I notated here. You see, we will talk very much about the hardware, the software flag, the variable, for example, a start transmission flag. That is nothing that a RAM memory position type char, where here you have the bit of interest, okay, 0 or 1. If you have a 1 here, if you have set this flag to be 1, you see, let me do that again here, bar start transmission flag equal 1. If you do that, okay, you are, when you come back after the interrupt to the main program, and for example, when you start again the loop here, you run the state logic, here you have this flag set to 1. And this means that perhaps you can go from one state to the other state, okay? Because this state transition depends on the value of the bar start flag to be 1, you see? So that's the dynamics, you know, that's the way it works in time.